Thanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are having the compiler design subject. As far as the previous episode is concerned, we have studied the shift-reduce parsing, so which is one of the simplest parsing which construct the parse tree in bottom to top approach. That means it constructs the parse tree from the leaf nodes towards the root. So it has 4 different actions, that is shifting the current token from the input, or accepting the current handle whatever is on the top of the stack, or it can be the accept action provided you are having no more tokens in the buffer and the dollar alone is on the that is the stack. So if none of this happens, then we will be calling the action as an erroneous action, so which will be that is reported to the programmer saying that something is wrong with the input. So this is what the parsing actions. So we have seen one example in the previous that is class also. We will be given a grammar. So we expect that the grammar is supposed to be an unambiguous grammar, so that the rightmost derivation construction will be that is deterministic, because the shift-reduce parser functions by constructing the rightmost derivation first, and it will be generating the right essential forms or the canonical reduction sequence by reversing the order of the right essential forms generated from the rightmost derivation. So that is actually we start with the start symbol of the grammar, and we will move towards the that is sentence which contains only terminals. But as far as the shift-reduce parsing is concerned, its parsing starts with that is the symbols which are available in the sentential form which is given for that is parsing, and we will move towards the root node of the parse tree. So which means that we have to have the sentential forms in the reverse direction, reverse order, so that the shift-reduce parsing will find out the handles and replace the handle by the appropriate left hand side of the production. That the process is actually called the handle pruning process. And continuously in each step of the sentential form, we will find a handle which is a substring which will be replaced by the corresponding left hand side of the production, for which this handle is the right hand side. And we will do this until we reach the start symbol of the grammar, that is going to be the root of the parse tree. So this is what the process being happening as far as shift-reduce parsing is concerned. So even today also we are having one simple example where we can see that how the parsing or shift-reduce parsing is going to happen. That means how we are constructing the rightmost derivation for the given sentence, which is supposed to be a string in the language of the grammar, and followed by that is the canonical reduction sequence construction, or it is going to be the handle pruning process. So then we shall see how the string is going to be parsed with the help of the that is the stack. We will be having, in general we know that there is a structure for the parser which has a stack, then a buffer, and there will be a driver program which will be consulting what is on the top of the stack and what is the current input symbol. Based on that the parsing actions will be carried out. So here is the given grammar. We have this S derives A, or it is cap symbol, or can be open bracket T closing bracket. And one more rule is the T is T comma that is S or S. So this is actually the grammar for the list structure. So one of the string is opening bracket A comma opening bracket A comma A closing bracket closing bracket. So this is the grammar. So we know that this is a bottom up parser, but as far as this grammar is concerned, it is a left recursive grammar. because of this T derives T is a rule, we claim that it is going to be a left recursive grammar. The left recursion is going to be an issue as far as the top down parser is concerned, but not for the bottom up parsers. So, even if your grammar has left recursion or left factoring, it is nothing wrong in proceeding with the bottom up parser. So, since shift reduce parsing is just a bottom up parser, the left recursion or left factoring problems in the grammar not necessarily be addressed. So, we can proceed with the grammar which has left recursion or even left factoring. So, in fact, we can even construct a shift reduce parser for the ambiguous grammar also, but when you are having the grammar in ambiguous version, so we know that there will be more than one rightmost derivation for a sentence if the sentence is going to be an ambiguous sentence. So, if you address that issue in the construction of the during the construction of the rightmost derivation itself, then even an ambiguous grammar is allowed as far as the shift reduce parsing is concerned. So, here we have the sentence. The sentence what we are supposed to parse by this grammar is opening bracket A, comma, opening bracket A, comma, A, closing bracket and then closing bracket, and these A's are the list elements, and then we are having the order that is how they are being grouped together. First, let us see that is how the rightmost derivation is constructed. So, this is going to be the start symbol of the grammar is yes, and it has actually three alternates. One is A, another one is cap, and followed by the opening bracket T, closing bracket. Since the given string to be parsed as opening bracket, closing bracket at the outer there is symbols. So, we must start with the third alternate for S, because of that we have S derives opening bracket T, closing bracket as the first step of your expansion of the start symbol of the grammar. And the second step, we know that it is going to have two number of list components inside the outer bracket. One is going to be A and another one is going to be another list inside bracket. So, since it is going to be two number of list components, we must expand this T by the T comma S. Suppose if you know that there will be only one list component, then straight away we can go for expanding this T by S and then S by A, so that we will be able to generate an A from the grammar. But whereas this string is concerned, so we know that it is having opening bracket A, comma, then another list element, that is opening bracket A comma A, closing bracket. So, there is a need for expanding this T by T comma S, and since it is going to be a rightmost derivation, since we are having two number of that is variables, and also we are interested in constructing only the rightmost derivation. So, this S is to be expanded, and as far as the string is concerned, it has two number of list elements, one is an atom and another one is another list. So, there is a need for expanding this S by another list item. So, for that we will go for expanding this S once again by the third alternate for S, that is going to be opening bracket T, closing bracket. So, we have opening bracket T, comma, opening bracket T, closing bracket as in the third step. So, now we go for once again a rightmost derivation from that is to form the next right initial form. The next right initial form, actually we have to expand this T is not an item, that is atom, but it is going to be list of elements. So, since it is having A comma A, we must expand this T by once again T comma S. So, we have T comma S. So, this is that is the initial form we have obtained after expanding this T by T comma S, then this S by T, then T by once again T comma S. So, now we have the pattern almost matched. So, we want to have a that is list of items which has two number of there is elements inside, one is an atom, another one is another list, and within that list we are having two elements, one is T and another one is going to be S. So, now it is a matter of just replacing those variables available in the grammar by the respective that is unique variables, so that we will be able to generate the string A comma A comma A. So, what happens here is this S is now replaced by A because of the rule number 1, and then T comma S comma A is the result because of the T is expanded to S. So, then S will be expanded by A, and then this T will be expanded by once again S, and finally we will be having opening bracket A comma opening bracket A comma A, closing bracket and closing bracket. So, since we are able to find out the there is rightmost derivation for the string, that is opening bracket a comma opening bracket a comma a closing bracket, we can say that this is a string, valid string, which could be parsed by the shift reduce parser as it is available in the language of this grammar. So, the next thing is that is the handle pruning process. Since you already constructed the rightmost derivation, we can even go for constructing the handle pruning process. So, the handle pruning process is otherwise called as the canonical reduction sequence of that is generation. So, which has 3 columns. For the first column we write the right sequential form, but in the reverse order in which they are generated from the rightmost derivation, and in every step of the sequential form we will find out the handle that is handled by the reducing production, whatever is applicable for that. So, let us see that is what is the first sequential form. The first sequential form is the last sequential form as far as the rightmost derivation is concerned, which has exclusively only terminals. So, we have that is opening bracket a comma opening bracket a comma opening, that is a closing bracket closing bracket. So, as far as the previous sequential form is concerned, so we had opening bracket s followed by the rest of the things. So, from this what do we understand is, so this a which is colored one is replaced by this s or reduced by this s. So, what we should do here now is identify the handle. The handle is a, which has been changed in color, and the reducing production is going to be s derives a. And what should be done now is, so you replace the a which has been identified in the sequential form by the corresponding left hand side of the production. So, that is going to be a reducing production. So, you will be having opening bracket s comma opening bracket a comma a closing bracket and closing bracket. So, that is how we are getting the second sequential form from the first one by identifying the handle and the handle pruning. So, from the second one you can find out the change in the third one. The change in third one is this s has been replaced by t. So, what does it mean is s is going to be the handle and it has been replaced by t, but that is allowed only because of the reducing production t derives s. So, what should be done is you find out s and replace it by t, so that we will be having the next sequential form opening bracket t comma opening bracket a comma sorry closing bracket and closing bracket. So, now what do we do here is identifying the handle, which is a is identified as the handle, that is the handle, and reducing production is going to be s derives a, and then we will be having that is s here, and in the next step we go for identifying s as the handle, which will be replaced by t, then a is the handle which is replaced by s. So, now it is going to be t comma s is the handle. So far we are seeing that is a symbol as a handle, but time being, that is as far as this present context is concerned, we find t comma s as the entire handle. So, we have t comma s, the t comma s becomes the handle only because of there is a production t derives t comma s. So, now what happens is t comma s is going to be replaced by the left hand side of the same production, that is t. So, you will be having t comma s reduced to t. So, that is this step. And next step, so actually we are having t comma s, but it is to be converted into t comma opening bracket t closing bracket. So, for that we need to replace this that is what is happening is your s. So, your t comma s as t because of the rule t comma s reduced to t, and then this opening bracket t closing bracket becomes the whole handle. So, as it is stated here, opening bracket t and closing bracket. So, now this opening bracket t closing bracket is going to be reduced by s, since there exists a production s derives opening bracket t closing bracket. So, now we have t comma s here. Once again the same story, we find t comma s is going to be the that is a handle, that is your handle, and now what happens is we find left hand side for that t comma s, it is going to be t, and so we will be having reduction t comma s reduced to t. So, in the next step we find the whole opening bracket t closing bracket as the handle, and we go for that is the reduction S from opening bracket T and closing bracket. Finally, we are getting S as the that is the only symbol available in your right sequential form. So, this is how the handle pruning process is being carried out. So, we started with the entire sequential form, that is sequential form, or we can say that the string which is supposed to be parsed, and now we have reached the start symbol of the grammar. So, this reduction, that is from the complete sentence to the given start symbol of the grammar, is called the canonical reduction sequence. But as far as the parsing is concerned, there will be a stack involved, and the stack will take care of that is what will be the top and what is going to be the handle, and how the handle has been identified and how it is being replaced. So, finally, how do you say that it is going to be accepted? So, we shall see the stack implementation of the same string, but after a short break. Welcome back. We have seen the handle pruning process for the grammar which is meant for the list structures, that is the canonical reduction sequence, and in each step of the reduction sequence we identify the handle, and it is being replaced by the appropriate left hand side provided the handle is on the right hand side of the production. And now let us see that is how the stack implementation is going to happen in order to reduce create the parse tree in a bottom up manner. So, we know that the buffer is initially loaded with the entire string which is supposed to be parsed, or for which we need to construct the parse tree, and on the other side we will be having the stack which is initialized with the dollar, which is nothing but the bottom of the that is the stack, bottom end of the stack. Then we will be that is seeing that is on what each step what is going to be the action being carried out. So, we know it is going to be either a shift action or a reduce action. In the case of a reduce action, we should have identified a handle which is on top of the stack, and there will be a production for that which will be used for the reduction. And whenever we find that there is the start symbol is alone on the top of the stack and there is no more symbol on the buffer, we will go for declaring an accept state. So, if none of this happens, then we will go for declaring it as an error. So, here we have the implementation. So, actually this string being taken is going to be the opening bracket a comma then opening bracket a comma a closing bracket, and as usual it is going to be terminated by the terminal symbol called dollar. So, that is the end marker for the string. So, first what should be done? So, since we do not find out anything on the stack, the only possible action is the shift action. So, we go for a shift action. As a result of that, the first token from the buffer has been shifted onto the stack, and immediately we should see that is whether there is any handle available for reduction or not. And we do not find a handle which contains the only symbol opening bracket which is on the top of the stack as such. So, there is no question of going for a reduction now, and we will go for another shift to find out a valid handle on top of the stack. So, we go for shifting the next token. The next token is going to be A, and which will be that is you are on top of the stack as such now. So, now there is a chance for having a that is a handle, because we have a production which is called S derives A, on which the right hand side is going to be A. So, there is a chance for having or declaring this as a handle, but that should be decided whether it is it has been really a handle or not from the rightmost derivation or the canonical reduction sequence. And when you look at the canonical reduction sequence also, we find this is going to be a handle now, which will be replaced by the appropriate left hand side. So, we declare a reduce action now, that is going to be the reduce action by S derives that is A. So, what happens on the top of the stack A is that is it just pop it out and then push the left hand side of the production. The left hand side of the production is going to be S. So, we will be having dollar followed by opening bracket followed by that is S. So, next we can find out whether there is any more handle available on the top of the stack. Once again, by our canonical reduction sequence, the S is going to be the handle with a reducing production called T derives S. So, we will replace this S by T, For that we need to pop out S out of the stack and push T onto the stack. So, next what happens is, so we go for a shift action because we do not have a additional another task, and that is handle on top of the stack, because there is no reduction for T, or there is no reduction for even open bracket followed by T. So, what should be done is, the only action is going to be the shift action, which will take that opening bracket, the comma onto the top of the stack. No token has been identified now. So, we will go for another shift action, which will move opening bracket, no token. Then once again there is no handle, once again go for a shift action, we find A, which will be reduced to that is S, and then we will go for another reduction, which will replace this S by that is T. So, we will be having T comma opening bracket comma followed by a T. Then it is going to be shift action, because we did not find out any that is token or handle on top of the stack. It is going to be a comma, then S will be shifted, and it is going to be a will be shifted, then A gets reduced by S because of the reducing production, S derives A, and then it is going to be T comma S gets reduced by T. So, to get T comma opening bracket and T, and now we have that is opening bracket followed by T on top of the stack, which cannot be a valid handle. So, to make it as a valid handle, there is a need for a shift operation. So, it is going to be the closing bracket being shifted, which will give us the opening bracket T and the closing bracket. Now, we have a handle because of the reducing production, S derives opening bracket T and then closing bracket. So, what happens here is the opening bracket T closing bracket is replaced by S. So, to get T comma S as the next handle. So, we have T is equal to T comma S. So, what happens here is the T comma S gets reduced by T, and now opening bracket T, here is a closing bracket that will be moved on to the top of the stack to have opening bracket T and closing bracket. So, that is going to be your S derives opening bracket T closing bracket, and now it is going to be the S on top of the stack. So, we have dollar followed by S on stack and dollar alone on the buffer. So, that is the case which we have to declare an accept action. So, this is how the parsing is going to be done with the help of your stack implementation or stack. So, we started with the dollar alone on the stack, which denotes only the stack is an empty stack, and followed by initializing the complete string, which is to be passed onto the buffer, that is input buffer. So, then every time we find that is whether it is going to be shift action or it is going to be reduce action in consultation with what is going to happen as far as the canonical reduction sequence is concerned, or during the handle pruning process with the reverse of the rightmost derivation is concerned. So, finally, if you find that dollar with the start symbol on top of the stack and no more symbols on the buffer, we will say that the parsing action has been completed. So, the parsing is over and the accept action has been declared. So, one important thing to be understood here is that is when you are seeing the stack, every symbol available in the stack is going to be a node in the parse tree. So, it looks like a procedural representation, but actually it is a pictorial representation where we have a pointer from each that is symbol in the stack to the parse tree. So, every time, that is when you go for a shift action, we will be introducing a leaf node, and when you go for a reduce action, we will collect few leaf nodes, maybe one or more number of leaf nodes will be collected, and they will be that is combined to form a new tree with the left hand side of that production as the root and the symbols available on the right hand side. That means, the nodes which are just taken as part of the handle, they are going to be made as the children of that node. So, at the end, I said when we are having dollar followed by the start symbol on the stack and no more symbols on the buffer, it is going to be an accept action, which means that we have only, that is, the start symbol on the top of the stack or start symbol alone on the stack. So, it means the tree's root has been reached. So, it is a pointer for the root. So, and we do not find out any number of any that is symbol on the buffer. So, that is going to be the end of the parsing process. So, if you are not able to find out a handle on the top of the stack, or after finding something like some pattern, but we are not able to find out a reducing production, So, then in that case we will declare that is errors. So, here we do not mind out errors, because as the string what we are given as going to be a valid string which is there in the language of the grammar, and that is what we have the accept action at the end. So, that is about the shift reduce parsing, and now we have that is the next parsing technique which we call it as the operator precedence parsing. So, that is also going to be a bottom up parser. Since it is going to be a bottom up parser, we should understand that the parse tree is going to be constructed in a bottom to top approach. So, we will collect the leaf nodes and we will decide the parsing action, whether it is going to be a shift action or reduce action or accept action, and finally we will be left with only the root node of the parse tree with no symbol on the buffer, which means that the string has been accepted or the parsing has been completely constructed. But as far as operator precedence parsing is concerned, so we wanted to have a that is a grammar which is called as the operator grammar. So, with there is only this operator grammar we will be able to do the operator precedence parsing. So, if you go for any grammar other than operator grammar, then this operator precedence parsing will not work for us. First you should know what is the meaning of an operator grammar. So, the meaning is here, or definition is a grammar with no productions having two consecutive non-terminals, that is what. So, you take the right hand side of any production and we can have two consecutive terminals, or we can have two terminals separated by a variable, but no question of having two consecutive variables. So, if it is going to be satisfied by that is all the productions available in the grammar, then the grammar can be called as an operator precedence, that is operator grammar. So, what happens here is the precedence relation, we will be defining precedence relation, something like three precedence relations are given for us. One is going to be the precedentially less than, and another one is greater than and equal precedence. So, these three precedence relations will be defined among in between, that is every pair of there is operators. So, the operators here not necessarily be always plus and minus, it can be any terminal, that is what we call it as the operators here. So, in between every pair of terminals we will be defining a relationship, either it can be precedentially less than or precedentially greater than or equally equal precedence among the operators. So, if it is there and it is going to be disjoint, so then we will be calling it as an operator precedence grammar. So, it is going to be the definition for operator precedence grammar. We have it is an epsilon pre operator grammar, which means that there is no question of having an epsilon on the right hand side of any production, that is the first condition, and the relation, that is your relations, there is in between every pair of the operators or the terminals. So, these relations must be completely disjoint. So, then we can claim that it is going to be an operator precedence grammar. So, the three relations are one is the less than, which says that when A is precedentially less than B, the meaning is A gives precedence to that is B, that is A is giving more precedence for B, and another one is A equals B, A is precedentially equal to B, which says that A and B have the same precedence, and the third one is we have that is A greater than B, which says that A takes the precedence over B. So, when we find A and B together, that is in the order, that is A followed by B. So, A is supposed to be reduced even before B gets shifted onto the stack, because of A is precedentially having more value than this B. So, you can have one simple example, here it is the operator grammar. So, we know that it is going to be the expression grammar, one with there is ambiguity and another one with unambiguous version. So, in both the cases we know that there is no question of having two consecutive variables anywhere. So, E and E separated by plus, and E and E separated by star, and E and E separated by exponentiation operation, and here we are having two consecutive terminals, but in between them we are having that is a variable called E, and the same thing is true even here also. So, we have, but the grammar is going to be an unambiguous version. So, E plus T, and here we have only one variable. So, we can have one variable or one terminal or number of terminals together, but no question of having two consecutive variables. So, even in this grammar also we do not have any that is case with the two consecutive variables. So, we can say that this grammar is going to be an that is operator grammar. So, as far as this episode is concerned, we have seen one more example for shift reduce parsing. There is a grammar for list structures, and we have seen that is how the grammar is used for constructing the rightmost derivation for the given sentence, then canonical reduction sequence, and followed by the stack implementation for the string, which is equivalent to constructing the predict. So, the parser, that is your parse tree in bottom to top manner. And also we have seen what is going to be the operator grammar. So, when you are having a grammar whose right hand side does not have two consecutive variables at any cost, then the grammar becomes operator grammar, and it is possible to define the precedence relation among the various operators, and if these relations are going to be unique, then we will be calling the grammar as operator precedence grammar. So, this is what we have seen as far as this episode is concerned, and you may be there is given there is any context free grammar for shift reduce parsing with particular string, there is any one of the string out of that, and we have to show that how the parse tree is going to be constructed in a bottom up manner, and what is the meaning of an operator grammar, and how the precedence among the operators are identified. There are two methods, one is by the precedence information, and another one is with the help of constructing the parse tree. So, these are all the possible questions as far as this particular episode is concerned. So, with this I complete this episode. Thank you all.